Okay, going to have a bit of a recap on complex numbers. So when we look at the first slide on this presentation, which you have in Classroom, we can see that we've got a quadratic equation, x squared minus 4x plus 13 equals 0. And here we have the formula that you all recognise, hopefully. And all we've got to do is put the a, the b and the c values in. So a in this case is 1, b is 4 and c is 13. Put those numbers in, crunch it down, and we end up with this at the bottom. Okay, so don't worry too much about how we get from here to here. That's just sort of a separate session. But this one here leaves us with this problem here. We've got 2 plus or minus the square root of minus 1 times 3. Now we know that you can't have the square root of a minus number because minus 1 times minus 1 is 1 and 1 times 1 is 1. So there's no such thing as a square root of a minus number. So we have to do something with that. It's there, we can't ignore it, but we have to do something with it. So what we do is we assign it the letter j. Okay, so we call it j, and we can substitute wherever it says the square root of minus 1, we can substitute j in, and then we can just leave it there while we deal with it, and we can deal with it. Just as a separate note, in traditional maths we use I as opposed to engineering maths where we use j, and the reason we use j in engineering maths is that I is the value for instantaneous current, so it could get a little bit confusing if you had two i's in a mathematical expression and one was current and one was this replacement, so we make it j. So looking back at this expression we had on the previous slide, we've now got 2 plus or minus the square root of minus 1 times 3, and we just replace the square root of minus 1 with j, so now we end up with 2 plus or minus j3. The solution to a quadratic equation has two solutions, so we've got 2 plus j3 and 2 minus j3, and that's because of this bit here. Okay, and these are complex numbers because they've got this j in them. Okay, and we've got two elements to a complex number. One is the real part and one is the imaginary part, and obviously we mustn't ignore the sign, but just for now the real number is the 2 and the imaginary part is the j3. So this form now, which is x plus jy, if we put it in an algebraic form, is an algebraic form, but it can also be called the Cartesian form. Cartesian is a derivation of maps, and that will make a bit more sense when we start doing Argand diagrams. And it's also known as rectangular notation. So now we look at powers of j. So it's convenient for us to look at powers of j because ultimately we're parking the j in the expression. We can't do anything with it until we start doing this, and once we do this we can actually get rid of the j. Okay, so that's really what we're doing here. So we start off with the proof that we made earlier, which is that j equals minus 1. And so if we do j squared, and this is the most important one that we need to know, we then say that j squared is the same as the square root of minus 1 squared, and the square root of minus 1 squared is minus 1. So if you're not sure about that, have a look up here. Here's the square root of 4, and the square root of 4 is 2, and 2 squared is 4. And if we do the same thing here, the square root of 36 is 6, and 6 squared is 36. So the square of a square root is the number that's inside here. Yeah. So if we follow that logic here, we can see that the square root of minus 1 squared is minus 1. And there are other proofs then. We've got j cubed, so j cubed is j squared times j, and that becomes minus 1 times j is equal to minus j. And j to the 4 is j squared squared, which is minus 1 squared, which is 1. And j to the 5 equals j to the power of 4 times j, which is, well, j to the 4 is 1, we did that here, and j is j, so j to the power of 5 is j. And then j to the 6 is j squared to the power of 3, if you can see that. So if you remember your power rules, a power to the power of a power is 2 times 3, so j to the 6 is j to the 2 to the 3. J squared we know is minus 1, so we've got minus 1 cubed, and minus 1 cubed is minus 1, because minus 1 times minus 1 is 1 times minus 1 is minus 1. So these proofs are ways of dealing with j, and some of these lead us to simple numbers, and what we want to do is try and get these j's into a form where we can dispense of them by just turning them into a number, a real number if you like. So we can add them. they're numbers. The process is a little bit more complicated, I suppose, than normal addition, but the adding up bit is fairly straightforward. So the first one we do is got to get rid of the brackets. We've got some fairly simple brackets here. We've got 3 plus j2 plus 5 plus j6. Now in this case we can just get rid of the brackets because everything is plus, and you need to remember that for the next one when we're doing subtraction, but everything is plus, so we can just get rid of the brackets. So it's 3 plus j2 plus 5 plus j6, and then as in all algebraic expressions we collect all the like terms together. So we've got a 3 and a 5, so we can add the 3 plus the 5, so that becomes 8, and then we've got plus j2 and plus j6, so plus j2 plus j6 is plus j8, and it's as simple as that. So now we're going to look at subtraction. So subtraction is the same, but I've complicated it a bit this time by having a minus here between the two brackets, and that has an effect on the second bracket. That's because of basic mathematical principles. But if we go back to this one first, we can say 1 minus j2, and we just simply write that down here. Now you'll see that this has become plus 4, and it's because this bracket, this minus, affects everything inside the bracket individually. So it's minus 4, so that becomes plus 4, and then it's minus plus j, so it becomes minus j. So it's the easiest way I think about this is there's a 1 in here, a 1 there, so it's minus 1 times minus 4 and minus 1 times plus j, and that changes the signs. So this isn't a complex numbers thing, this is a expanding brackets thing, but in complex numbers this probably would cause the most confusion. So just to reiterate, we've now got 1 minus j2, we've now got plus 4 because of the effect of the minus and the minus, and we've got minus j because of the minus and the plus. So now then we've got an expression with no brackets in it, and again we can just collect like terms together. So 1 plus 4 is 5, and minus j2 minus j is minus j3. If you're going to kind of ignore the j if you want, you can say that would be minus 2 minus 1 would be minus 3, and then you can just put the j back in if that helps. But it's because it's basically minus 2 minus 1. But it's useful to get used to manipulating it with the j in it. So 1 plus 4 is 5, minus j2 minus j is minus j3, and that's subtraction. So here we've got an example from the BTEC book, and if you're not sure what it is, just go have a look. So let's go to your classroom, which is here. And if we go down to classwork, scroll down to complex numbers, bottom one there, you can see there's the text. And this should be question 6.1 A, I think. And it says, if Z1, Z2 and Z3 represent three complex numbers such as that, that and that, find the complex numbers which represent. So the first one is Z1 plus Z2 plus Z3. Okay. So that's where that's come from if you want to go and look at it. So I'm not going to go over this because we went over it in class. The working out is here. Here are the three numbers written out. Here is the problem. Here is me writing it in brackets. I've expanded out the bracket and then I've come up with the answer. Okay, so you just need to work through that on your own. Make sure you work through this one and have a practice. Now it's fairly simple, this one, because all of the signs in the middle are pluses, so none of the signs change. You simply open out the brackets and just add them all up. Okay, this is the next one. Slightly more complicated because you're subtracting, and again I'm not going to go through this. This is the next one in the book and you can follow that through yourself. And if you look at the numbers here, you've got a minus here and a minus here, so that minus makes that 4.3 a minus, and it makes this minus j 0.6 a plus. Okay, so the sign for that changes to that because of this minus. So minus times a plus is a minus, and minus times a minus is a plus. Okay, so that's just, this is the only thing you have to do that's a little bit tricky with these, is just when you're expanding out these brackets, just watch this sign, okay, and the effect it has on the one in the middle, and then it's just a case of adding the 1.6 plus minus 4.3 plus 1.1, so it's 1.6 minus 4.3 plus 1.1, and the same one here, j 2.3 plus j 0.6 plus j 0.9. Add those up and it's there. Okay, I can't remember why this is on the slides. This is the record of the stuff we did in class. I think this was me going through a problem, but have a work through that one. Again, looks fairly straightforward. So multiplication is a fairly straightforward process. Only we can start now making use of this j squared identity that we discovered earlier. So let's have a quick recap of this one. We've got 3 plus j2 times 4 plus j. So the multiplication of the brackets is the same as if you're multiplying two brackets when you're doing quadratic equations. It's the same, or factorising. It's the same process. You multiply each term in each bracket by each other, and you end up with 3 times 4 is 12. 3 times j is j3. j2 times 4 is j8. And j2 times j is j squared 2. Okay, so we multiply the j by the j, and then it's 2. So if this was x, it would say 2x squared, but we'll just write it down like this, j squared 2. And what we can immediately then, we can rewrite it. We can say 12 plus j11, because j3 plus j8 is j11. And then we can replace the j squared, because we identified earlier that the j squared is the same as -1, with a -1. And then it becomes plus -1 times 2, which is -2. So then we have 12 plus j11 minus 2, so it's 12 minus 2 is 10 plus j11. So that's the multiplication process. So here we introduce the concept of the conjugate, which is the opposite, if you like, of a complex, or the opposite type of complex number to the one you're interested in. So the one we're interested in this case is 3 plus j4, and the conjugate is 3 minus j4. And what this conjugate does, if we multiply the original number by its conjugate, we end up with a number. So this is another way of getting rid of the j, so we end up with something we can actually do something with. So in this case here, we multiply out the brackets, and we end up with 9 minus j12 plus j12, because it's 3 times 3 is 9. 3 times minus j4 is minus j12. Minus j4 times 3 is plus j12, and then we end up with minus j squared 16, which is j times j is j squared, or minus j squared, because it's plus j times minus j. And then we've got plus 4 times minus 4, so that's 4 times 4 is 16, so it's minus j squared 16. Okay, so because again we know that j squared is -1, it becomes minus 1 times 16, so that becomes 9. So that would then become 9 minus 16, which is 9 plus 16, which is 25. So because we've used this conjugate, what we've done is we've got rid of the j term altogether. Okay, so now we end up with the number 25. So multiplying that by that is going to give you the answer 25. Now the reason we do that is it allows us to manipulate divisions, which is what I'm going to cover next. So that's going to be in the next video, because I'm getting close to 15 minutes on this one. Okay, so see you on the next video.